Hi everyone. In this video we will go over problem F that appeared in CodeCraft 2022. It is called K-set tree. You are given a tree G with n vertices and an integer k. The vertices of the tree are numbered 1 to n. For a root R and a subset of vertices of G such that the size of the subset is k, we define a function f of R and S as the size of the smallest subtree containing all the vertices in S. Now let us see what f of R comma S means. You can observe that R is an input to the function, which means that for a particular value of f of R comma S, the root is fixed. Alright, so let's assume that there is a tree rooted at R, and let's assume that k is equal to 2, that is the size of the subset is 2. So let's take these two nodes. Let's assume that these two nodes is one subset of the entire set of nodes. Now what is the smallest size of the tree, of a subtree, such that these two nodes are contained within it? We can see that this subtree over here is the smallest subtree such that it contains these two nodes. And what will be the value of f of R comma S, where S is the set of these two nodes? It will be the size of such smallest subtree, that is f of R comma S is equal to 2, it is equal to 5 in this case. Now let us take some other nodes. Let's say that we choose this particular node and this particular node. Again, what is the smallest subtree that contains these two nodes? It is this, and in this case f of R comma S is equal to 4. So this is the definition of f of R comma S. So we have to calculate this particular expression, that is the sum of f of R comma S for all distinct combinations of possible roots and the possible subsets. Notice that the root has to be fixed for the calculation of this particular expression f of R comma S. So first let's divide this term into two parts. We will try to calculate this sigma first, and then we will later on worry about how can we calculate it for all possible roots. That is, we will root our tree at a particular value R and calculate the internal sigma first. So let us solve this problem now. What we have to do is we have to find the sum of f of R comma S for all the possible subsets of size k, and the root is fixed. So let us draw a rooted tree over here. Over here the root is fixed to be R, and accordingly there is some tree that spans below. Now let's assume that there is some node here and some node over here and maybe some node over here. Whatever the value of k is, the nodes are such that the minimum size subtree that we want comes out to be this, right? So what is the subtree size? Over here it is 1 2 3 4 5, that is f of R comma S equals 5. Now there will exist some other subset also. Maybe let's denote it by red. Maybe this node, and then let's say this particular node. This also has the same subtree as the smallest subtree that covers the entire set. So the value for that is also going to be 5. So instead of calculating the values differently for every set, let's solve a different problem. Let's look at the subtree itself and let's try to count the number of subsets possible such that this particular subtree is going to be the smallest subtree that covers that set. So let's now calculate this. Let us assume that we have some node V over here, that is some node in our entire tree, and we are focusing on the subtree of V right now. So what we can observe is that if in our entire subset that we are trying to choose, if some value exists in this particular branch of the tree, and then some value exists, some node exists in some other branch of the tree, then the entire subtree will be the smallest subtree that contains those two nodes. And then maybe if we take some node in some branch and some other node in the same branch, but then there is a node that is the node V itself. In that case also the smallest subtree that covers our subset will be the entire tree. Now when will it be that the subtree, the smallest subtree that covers our entire set is not this subtree that we're talking about? That will be only in the case when all the nodes are in only one single branch. That is, if all the nodes are suppose in this branch, then the size of the subtree will be different. It will be the subtree of the child, right? If there is at least one node that is in some other branch, in that case the only way to connect those two nodes is through the root itself, the root of the subtree. That is why the entire subtree becomes the smallest subtree that contains those nodes. Now how do we count such subsets such that the smallest size is this particular subtree that we're talking about? That can be done using combinatorics. So we want to calculate the total number of subsets of size k such that this particular subtree is the smallest subtree that covers the set. So let's first calculate the total number of subsets of size k among this entire subtree. That is going to be size of u choose, this will be v, choose k. This is the total number of subsets of size k that are there in the entire subtree. Now to calculate those particular subsets that have the property that this subtree is the smallest subtree that contains it, we will need to subtract all the subsets of size k that occur in the branches over here. Once we remove the subsets of size k that occur only in this branch and only in this branch and only in this branch, then the remaining number of subsets will be the subsets such that the property that we want is satisfied. So we will simply subtract all the subsets that we don't want. That will be size of u, assuming that u is a child. So u belongs to children. Choose k. That is, we're removing all the subsets of size k that are occurring in the branches. Let's call this value count of v. That is, it is the count of the subsets of size k such that the subtree of v is the smallest subtree that covers that set. Now what was f of r comma s again? It was the size of the smallest subtree such that this subtree contains the set S. We didn't exactly solve this problem, we solved a slightly different problem as I said before. What we did was we took a subtree and we counted how many sets S exist in the subtree such that the size is equal to k, and they follow this property that we want. So to calculate f of r comma s from this value of count that we calculated, we simply need to do one thing, that is, if we take the count of v and multiply it by the size of v. Why the size? Because we have to calculate the size of the smallest subtree such that this subtree contains the set S. So for all the subsets S in this subtree, if you want to take the contribution towards f of r comma s, the sigma of f of r comma s that we're trying to calculate, we need to take the contribution of every such set, and every such set will have the contribution of size of v, right? So if we multiply these two terms, that will be the contribution of let's call this count of SZV. So this value will be the contribution of just the node V towards the entire sigma that we're trying to calculate. This was for all the sets V, subsets V, subsets of all the vertices, such that S is equal to K for a particular R, right? So count Z, CNT CZ SZ is the contribution of just the node V towards this sum. And now if we take the sum of all the count ZV's possible, that is, if we take sigma of V from 1 to n, we should get the value that we were trying to calculate. So now we know that this expression can be written as a different expression. And how do we calculate this? Let's quickly go over it. We will root our tree at a particular root r as said before, and then we will simply DFS over the tree. For each node of the tree, we will maintain three values. The first value that we will maintain will be the size of the subtree of that particular node. The second will be the count. This will be calculated using the combinatorics formula that we explained above. This can be calculated using a simple DP approach that I will not be covering. Just take the sum of those children and add that, and add 1 because of this node. And finally, the third property that we want to maintain is count Z of V, which is nothing but the product of the size of V and the count of V. And once this is done, we can calculate the sigma value that we're trying to calculate by taking the sum of all the count Z's for all the nodes. So now we have calculated the answer for just a particular value of R, but we want to calculate it for all distinct possible combinations of the roots R and the subsets S. How do we do that? We will do that using something called the rerouting technique. So how do we go about it? Remember, we stored three values for every single node, right? What were those values? It was count, it was size, it was count SZ. Currently our root is this, that is small r. notice what happens when we try to change the root from this particular value to one of its neighbors, that is this. Let's call this nr, that is new root, and instead of r we'll call this or, that is old root. You can see that the properties for all these subtrees and all these nodes will remain the same. These three properties will remain the same for all these nodes. They will only change for the old root and the new root. And we can recalculate these properties just by using their children values. And then we will obtain another rooted tree which is rooted at nr, while or is a child of nr. And the remaining tree remains the same. And now, since we have already calculated the values for nr, the new values for nr and or, we can calculate the answer efficiently for this particular rooted tree again, and then we can again further reroute it again to a different node and go over all the roots, all the nodes as roots, and then we can calculate the value for all the possible roots in this way. Let's now see how the properties change when we reroute from the old root to the new root. Let's first look at the size of the subtree. We can say that the size, the new size in fact, of the old root will change. Earlier it was equal to the size of the entire tree, that is n. Now it will be some smaller size, right? We can say that it is equal to size of old root, that is the old size of old root, minus, if we subtract the size of this particular branch, we will get the size of the newer subtree of or. So we can say that the new size of the old root is the old size of the old root minus the old size of the new root. And we can also say the size of the new size of the new root is equal to capital N, that is the entire size of the tree. Let's see how we can recalculate the count value. This was the formula of count. Now you can see that there are two terms in this. One is the size of v, and then there is contribution by the size of the children. So let's talk about the old root first. We want to recalculate the count value, that is count new of the old root. We can see that the size contributes towards it. Now, since the size of old root has changed, we need to remove the contribution of the old size and put back the contribution of the new size. That is, we will say that count of new of old root is equal to count of old root. From this, we will subtract the contribution of the size that was there before, that is size old v, choose k, and then we will add the contribution of the newer size, that is size new of v. Actually this will not be v, it should be or, that stands for the old root. Choose k, and you can see that the old root is now losing a child that it had before. It doesn't have that child anymore, so we need to remove the contribution of that as well. So we will actually add the size of, that is the size old. We need to remove this contribution, so we will remove that the size old of the new root, choose k. While removing, we will actually add it because earlier we were subtracting it. Similarly, we want to calculate the count value, the new count value for the new root. For that, we will make some edits to the old count value of the new root. What edits will we make? We will again follow the same method of we will remove the contribution of the old size and add back the contribution of the new size. So we will subtract size of old of new root, choose k, and we will add back the size of new root, choose k. And then you can see that when we are rerouting it, this new root is gaining a new child itself. So we need to account for that as well. For that, we will have to subtract the contribution of this, since in the formula we need to subtract it. So we will subtract size new of old root, choose k. And now the third property we have to recalculate is the count size property, that is the product. That can be simply calculated using the formula, that is count sz of new of old root will simply be count of, that is the new count of the old root, multiplied by the size, the new size of the old root, and count sz new of the new root will be the new count of the new root multiplied by the size, that is the new size of the new root. And finally, now we need to recalculate the answer using the new values. So if you remember earlier, what was our answer? Our answer was the sum of count z, sz of v for all v values. Let's call this answer of v. Alright, now we need to recalculate this answer of v using the new values that we've calculated. So we can say that answer of new root is equal to the answer of old root. From that, we need to subtract the contributions of the old nodes that we had, and we need to then add the contributions of the two new nodes that we have. So we will subtract count z old of or and subtract the count sz of new of the nr node, and then correspondingly we will add the count sz new of the old root and add the count sz new of the new root. The value that we get over here is answer nr, that is the internal sigma value that we were trying to calculate when r is equal to nr, that is sigma of f for r equals nr comma s, where s is a subset of all the set of vertices and the size of s is equal to k. So we have calculated the answer for a new value by using a small variation, a small change while rerouting that can be done in O of 1 operation, in O of 1 time complexity I meant. So finally, what will be our final answer that we are trying to calculate? which is supposed to be in the sigma over here above it for all the possible roots, right? That will simply be the sum of all answer of b from b equal to 1 to n. So we will use a rerouting technique in a DFS approach, and we will continuously keep rerouting whenever we go to a new node, and we will individually calculate a new answer in O of 1 time, and then the sum of all these answers will give us the final value that we're trying to calculate. That is it.